Hello and welcome. We are Group 12. My name is Gabriel Mendoza. My partners are Nicholas Roberts, Anthony Su, and Hung Wu. Today, we'll be going over counting operations, specifically an introduction to the analysis of algorithms. And here we go. Sit back, get some food, enjoy the ride. Love math. So the first question, right? What is an algorithm? And we've taken different approaches to answer this question. We know that an algorithm is a systematic procedure designed to implement a particular task. What that really just means it's how to solve a problem. But as computer science students, a majority of us are, an algorithm is a finite sequence of well-defined, computer implementable instructions, typically to solve a class of problems or to perform a computation. An algorithm consists of three things, right? So it has to be terminated, definitive, and doable, meaning we have to be able to apply it to something. So it's in layman terms, once again, it's how to solve a problem. Throughout class, we've dealt with matrices and vectors, and we wanted to show you what a small little application of a vector is. So we are given two vectors, and we are questioned to find an algorithm, calculate their dot product, and assume their dot product is defined. And we're given vector A as well as a vector B. So we know that the first step is to take the first element of the first vector and multiply it by the first element of the second vector. And we have to do the same all the way until we reach A of n times B of n. And we will add all the products together, and the result is a dot product between these two vectors. I think we've all seen this before. Oh, sorry. So, right, step by step is the definitive process. Addition, multiplication fulfills the effectiveness. And after the step 5, the result in the addition, the algorithm is terminated. So why do we need to analyze algorithms? So the reason we analyze is to find out the efficiency of algorithms. As computer science students, we find the complexity and space complexity. There's different cases. There's a best case, worst case, and average case. We usually go with the worst case. And in layman terms, once again, it's to examine the time of a particular approach to solve a problem and what's required to have that result. How do we do it? Time complexity wise, we do it by counting operations, and counting operation we'll go over what is established or is a counting operation. But like I said, we will go with the worst case, and that's denoted by the big O of the leading variable, for example, n plus 10, which is the big O of n. So operations, what are they? It's a step required to solve a problem. Counting operations, we've said it's to find the exact number of steps, calculations, assignments, comparisons, etc. It's not just the number of steps, it's the exact number of steps. So we see in this little algorithm here, we have 3 steps. We add 3 to row 1, and then after that addition, we add another 3 to row 1. We have to repeat the second process a minus 1 times. So the real complexity of this is a minus 1 plus 1, which is just a. That's it for my slides. I will hand it over to Anthony, who will go through applications of matrices through Gauss-Jordan and Gaussian elimination. You there, Anthony? Oh, it is.
So I'll be going to example with a matrix of Gaussian elimination. First off, we had to take it to row echelon form by making the diagonals 1s and making the bottoms of 0s. And then for each operation, it'll increment by 1. So after all these steps, going from this order, this will end up becoming 1s and 0s, and the rest could be changed as well. And as we head further, this one will be Gauss-Jordan elimination. This will take it a little bit further to reduce row echelon form, which makes these upper numbers to zeros and changes the outcome at the end. So what our question was, what do your answers suggest about the relative efficiency of the two algorithms? We said that the Gaussian elimination algorithm is faster than Gauss-Jordan. I'll be handing this back to Nico.
All right. From Anthony's specific example of Gaussian elimination, it's important to not only understand specific examples to understand each step or operation, but it's also important to understand the general form of the elimination. So that is what I'll be doing today. The first step is to show matrix A is an n by n matrix composed of aij entries, as shown here. To create the leading one requires n operations. As you can see, to do that, we multiply by the first entry, A11's reciprocal, and multiply the first row throughout that. So the first entry, A11, will be a 1, and the rest will just be some constants of those steps. So for each column will be one step all the way to n columns. Similarly, to create the first leading 0, we use elementary row operation 3, multiplication of a row added to another to replace that row. As you can see, has a similar number of steps to create the leading 0. And the rest in each column are just some other constants based on that row operation. Next, we can show to sweep out the entire first column and replace with zeros, except for the leading one in entry A11, requires A times n minus 1 operations. We can do that by showing we have already determined it takes n operations to create 1 0 in the first column. So it follows that since we've created 1 0 here, and we know it costs n operations, for each row we go down, we need to multiply it by that row. So the second 0 will be n times 2, n times 3, etc., until we reach n times n minus 1. And it's n minus 1 because we do not count the creation of this leading 1 for now. This is just the sweeping out of the first column for zeros. The number of operations thus is n times n minus 1. All right, once we've shown that, we can show the total of number of operations needed to reach row echelon form, which is going to look similar to Anthony's specific example he showed us earlier. So to do that, to create that diagonal of 1s with zeros underneath them, we perform that operation we saw in the previous slide. To sweep out the zeros is n times n minus 1. We add n to this operation because we need to consider the leading 1. So that would be the first column. Column 2, we reduce the number of operations by 1 to create the diagonal. So it follows that all the way to column n minus 1 is 2 plus 1 times 2. And then finally, the nth column is 1 operation. So the summation of that is this expression. Simplified is n squared plus n minus 1 squared, etc., to 1 squared. So now we can show the number of operations needed to complete the back substitution, because we now have the diagonal of 1s in reduced echelon form. So to do that, we need to start at the last entry of the column right here. And we start with that, seeing how each one represents a variable in our matrix equal to the augmented matrix here. And we can do that with subbing in the values. For the bottom or nth row, no operation needs to be done. N minus 1 row, we have to plug in our previous value into that equation. So that requires one operation. And then as you can see, as we go up to row 1, we have to increase the number of substitutions. So the number of operations is the sequence or summation 1 plus 2, etc. to n minus 1. So the total number of operations used by Gaussian elimination is these two summations added together. Here are the formulas. Adding them together equals this expression. Simplification yields the number of operations in total is n cubed divided by 3 plus n squared plus negative 1/3 times n. Now I will hand it over to Hung. Hung, you're muted.
Okay, so we already know that for Gaussian Jordan elimination, it will be always slower than Gaussian elimination. And in the next slides, I will explain why is that. So here we have our original matrix here, and from Nico's slide, we know that to get the leading one in the first row and all of the zero below that first leading one, we will have this amount of operation. And similarly, for the second row, to have the first leading one and all of the zero below that leading one, we will have this amount of operation. But let's say because to get reduced row echelon form, we assume that we always need to get all of the zero below and upper of the leading one as we go. So here, how much operation we need to get the upper zero here. So you see, to get the first leading one, we will need n operation in the first row. When we need zero here, that means we just minus one operation from that, and this lead to in this step we will have n minus one more operation compared to Gaussian elimination. We will repeatedly do that as we go, and just from an observation, we will know that we add 1 times n minus 1 more operation compared to Gauss elimination. That is the amount here, n minus 1. But why do we have the multiplication of 1 here? So let's say as we go to row 3, we will have this small amount of operation compared to Gauss elimination. So why do we have 2 times n minus 2 here? Just let's say at row 3, we will need to zero above the leading one. So that's why we will have 2 times here, because it's 2 rows. So we need the multiplier here. But why is n minus 2? Just with the same analogy, because for the first leading one, we will need an operation, right? And now we need to reduce amount that by the 2 zeros here. The first one is here, and the second one 0 will be in this place. So it will be n minus 2. And just as we go to the last row, it will become n minus 1 times this amount here. That is for the last row. So here's the calculation to find the delta between the two methods. From the formula we have here, the last line here, we put everything that is related to n to the left side, and for the right side is just everything that is numeric. With all of the n here, we factor out it, and then for all of these here, it will become something like the sum of first n squared. And for the left side, it's something like the sum of first n squared, and applying the formula that Nico showed in previous slides, we will have the equation here, and then finally we will have the result here. This is the difference between the two methods. So in other words, for Gauss elimination, we will have time complexity which is equal to this one, and for Gauss-Jordan elimination, the time complexity will be more than Gaussian elimination by this amount. And by the calculation here, it seems that the factor of the leading variable here has become 1/2. And with that said, we will see that for Gaussian elimination, the factor of big O here is 1/3. But for the Gauss-Jordan, the factor is 1/2. If it's a small number of n, then it wouldn't be a problem. But when we have like 1 billion, 1 trillion, then the factor of 2 and 3 here, 1/2 and 1/3 here, it will become a huge trouble. So that's why there is a time difference between the two elimination here. And for now, I will hand my slides to Nico so that he can demonstrate everything that by using the code.
All right. It's all fine and good to show the general big O notation of those two elimination processes. This is an application of those runtimes in a program. So here is the code for the Gaussian elimination. As you can see, it is a triple for loop, which reflects the n squared and the necessary swaps here. For Gauss-Jordan, we similarly have 3 for loops to reflect n cubed. But as you can see, there's going to be more if checks and more operations needed to create the ones both above and below those zeros. So I'm going to show the difference of the time complexities in 4 different matrices. So let me run this program. As you can see, Gauss-Jordan for a 3x3 is going to be 0 milliseconds, and it's going to be approximately both 0 milliseconds for both Gauss-Jordan and Gaussian, because it obviously takes a little bit of time, but it's so trivial that it just rounds to 0. For 100 by 100 matrix, you can see that it's 5 and 6 respectively, so not too bad. But as we keep increasing the size of the matrix, we can see that gap starting to widen, which reflects Hung's slides just previously. And then finally, when we reach the 1000 by 1000, we can see that it almost takes 2.4 seconds to do Gauss-Jordan elimination. So that's why our programs and softwares to do large systems of equation prefers to do Gaussian elimination, because the number of operations is significantly less. And with that, I will hand it back to Gabe.
Okay, my geniuses, you've gone through it. We've learned about, like I said, counting operations. We taught you a little bit about analysis of algorithms, their time complexity. And as well, we've compared the time complexity within the Gaussian elimination and Gauss-Jordan elimination. And we've concluded that Gaussian elimination is much faster than the Gauss-Jordan when, as Nico demonstrated, we can have huge 1,000 by 1,000 matrices, and we see this in applications in real life. We're not just met with a 3x3. And we'd like to thank you through sitting through our presentation. Once again, I am Gabriel Mendoza. My partners were Nicholas Roberts, Anthony Su, and Hung Bu. Once again, we thank you so much and love math. Bye-bye.